Okay, good morning. So first of all, I brought some copies of the paper I was mentioned to you about universal ratio. You might have a look. So there are you distributed So let me just summarize quickly where we are and what we want to achieve today. So we are essentially sitting at the fixed point where correlation length is infinity. At the fixed point, we admit that there is a complete set of scaling operator characterized by their scaling dimension delta n, and we make the hypothesis they are a basis, so any field can be expanded in terms of them. Then, from the fact that the correlation length is infinity, any two-point correlation function can be expressed in terms of local operator, and if I use this principle to the element of the basis, I have this relation, and this relation defines an operator product expansion algebra. And you can prove it. Actually, this is an exercise for you, that all expectation value of the scaling operator except the identity are going to be 0. Okay? So try to prove it. That being given, this means that the solution of the theory is provided once we are able to determine the structure constant, and once we are able to determine the spectrum of the operators. So, saying in a few words, the theory is solved once I'm able to identify the spectrum of the scaling operator, their anomalous dimension delta, their conformal dimension, and the structure constant which enter this operator product expansion. Because once I have this data, any correlation function of any fields, at the end of the day, will be expressed in terms of the expansion of the fields with respect to the basis. So here there are some. Once I reduce myself to correlation function of the basis, the correlation function of the basis by systematically taking the operator product expansion, I reduce the number of correlation I have to compute, n minus 1, n minus 2, n minus 3, and so on and so forth, collecting along the way all the bunch of structure constant. And at the end of the day, since all of them except the identity has vacuum expectation value, as a matter of fact, I have to determine what are the ways to lead to the identity. Okay? Is clear this concept? So morally, everything consists in reducing systematically the things until I got to the identity. So the main problem is indeed to determine these data, which are dynamical data, and conformal symmetry, in the way I specify in previous lecture, are not able to give us any clue, because for what conformal symmetry matter, any of these values is the same. I just use all what I can. So these are dynamical data. So in order to fix it, originally, I'm just saying historically, Polyakov, that has been the person that first has formulated the theory in this way, tried to solve this equation through the so-called bootstrap approach. Bootstrap approach means the following. Since it's an algebra, any algebra, in order to be consistent, from which the name bootstrap, has to be associative. Means that if I have three objects like this, should not be any ambiguity for what the final result is concerned, how I'm contracting. I contracted the first two and then the third one, or I contracted the last two and then the first one. Now, in terms of field theory, this property of associativity can be formulated in a very suggestive way in terms of the so-called duality of the 4-point function. So it's exactly the same. Associativity means, as I said, phi A, B, phi C. I can make these things and what remain contracted with this other one, but this has to be also equal to contract these things, so whatever happens, contract with this other one. Okay? So this is associativity. Now, as I said, a very suggestive way of expressing is through duality of 4-point functions. So this consists in the following. So you have a 4-point function of some external field phi A, phi B, phi C, phi D, position x1, x2, x3, and x4. So at this point, I can do the following. I can contract this field together and these fields together, and whatever I got is will be 2-point function that therefore I will contract between themselves, or I can contract A with C and B with D, and there should be no ambiguity in the final result. So graphically means that you can take this object and stretch either in this way or in this other way. Okay. So means that I shall have sum on kappa C A B kappa C C D kappa, or if you want L, phi kappa phi L, x2, x4. And this means essentially I've done these things. Sum on all the intermediate states. Okay? So I have A, B, C, D. I contract A, B with kappa, C, D with L, and then I have the propagator kappa and L. But this has to be equal to the one where I stretch in this other way, which I contract A with C, B with D, and these are dummy index kappa and L. So this has to be equal as well. Sum C A C kappa, C B D L, phi kappa, x2, x3, phi L, x4. Okay, clear? It's clear? And moreover, since correlator, I'm going to prove in 1 minute, this is some delta kappa L with some normalization, x2 minus x4, delta kappa plus delta L, and the same here. you see that this equation, so let me write down in full glory. So this equation that has to be true for the theory to be consistent, you can interpret as an equation for the structure constant and the anomalous dimension. Okay? It's clear? So I'm posing an algebra. I'm requiring the algebra is consistent. In order to be consistent, to be associative, means that all the coefficients to be proper balance in order to hold this identity. So that if you sum the intermediate states, conformal states, in the T channel, has to be equal to the sum of the conformal state in the S channel. Of course, the structure constant which enter in this channel are different in general. Okay?
So in the relationship written on the upper part,
yeah.
We are summing over K, so K shouldn't appear as an index in the result, right?
What do you mean? Are summing? I'm summing. Yeah, there will be, at the end of the day, there are some here.
In the very top one, so like,
Yeah.
if you are summing over K.
Yeah, and L.
And L.
K and L.
But they shouldn't feature in this, like, I think just the 2-point function is equal to delta K.
Yeah, the 2-point function is even, I'm saying this guy here, this one is equal to this one. So this was the ambitious goal of Polyakov in the late 70s, namely to build up consistent theory of the fixed point solving these equations. Now the goal turns out to be too ambitious, so it never succeeds and nobody else to crack directly the conformal field theory solving this equation. It's too hard because it's not linear, and moreover this anomalous dimension enters in a very funny way. So you have to, is an identity, by the way, that you cannot even solve perturbatively. It has to be true at once. You have no degrees of freedom what to do it. Okay? So the real way of solving conformal field theory turns out to be through a long journey on another way. Namely, turns out to be through the irreducible representation of the conformal algebra that we are going to define, hopefully today, finding the reducible representation of this algebra and see how the representation combine together to provide some consistency result. And once you do all this journey around, once you solve the theory, if you like, you can go and check explicitly that these equations are satisfied. Okay? So instead of facing directly the solution of this equation, which turns out to be too hard and too complicated, also you have no really way, no analytic way, no perturbative way, nothing. So either you are Euler to identify immediately what the solutions are, solution for an infinite number of parameters, which are C and the delta. So unless you are really a genius of mathematical identity of this type, this route turns out to be too difficult. So we'll follow different route, solving the equation through representation theory, and finally going and check the validity of this identity, which at the end of the day turns out to be identity which hold, for instance, for hypergeometric function. Because at the end of the day, there are theory of transcendental equations, and these are true for special class of functions.
Like you wrote up that the two-point function is a delta, but that's just a particular case. A delta case.
No, I will do today now.
Okay, the second thing, in the conformal bootstrap approach,
Yeah.
nowadays they still use the kind of equation, but they solve it numerically.
Yeah, okay. Thanks for the things. Yeah, you can focus the attention on this equation through additional commitment, additional required. So, for instance, you will see where the difficulties is. The difficulty is in the infinitely many descendant fields. This is the difficulty. That in 2 dimensions you have full control of it, in higher dimension much less. Okay, and so you can do some progress, and not, but require extra things, and there is no general way of doing this case by case. So, for instance, you have to pose some hypothesis on symmetry. You say you have a Z2 symmetry, therefore one field has to be odd, one has to be even. Composing 2 odd fields, I should have one even one. So there is some commitment, I have to say, and then you systematically kill the descendant in higher dimension, but it's an assumption. Here in 2 dimensions, you have full control of it. Okay? So far so good. So, the things I want to do, therefore, is start building the representation theory of the conformal algebra. I'm 2 dimension. I told you that I anticipated that in 2 dimension is useful to think our coordinate to be z and z bar disconnected from z, and seeing, and we will prove today, that indeed the theory for what algebra is concerned treat z and z bar separately. Okay, so give this for granted in order to write down equations which are much more simple than in the full glory. Okay, so what I want to prove is, first of all, some simple consequences of conformal invariance. On quasi primary fields. Okay, so primary fields, so I'm just using the z bar part. So if you want, let me write down the first time the full glory, but then I will skip the z bar part. So a quasi primary field is something which under Möbius transformation. Remember, Möbius is the only symmetry of the theory. So transformation of the coordinate according to this function has to be symmetry. The variation of the action is 0. So quasi-primary field of conformal weights delta and delta bar are those fields which under Möbius transformation transform as a generalized tensor of weight delta and delta bar, respectively with respect omega and omega bar. And I insist, omega bar and z bar has nothing to do with omega themselves, just different function, and I denote in this way. So these are the quasi-primary. The primary field are those which under generic transformation, generic analytic transformation, transform as tensor of weight delta and delta bar. Okay? These are definitions. So obviously a primary field is a quasi-primary field, is not true the vice versa. Okay? So I told you the reason to focus the attention on these fields is that they turns out, as we'll prove probably today, that they are really the building block of the conformal representations. So are vector more privileged than the other because using them I can build easily the irreducible representation. Okay? So this is the reason for doing that. Of course, you should have developed a little bit the theory to reach to this result. So that being said, I want to prove now that conformal invariance, alias if I exploit just this transformation, imply a very, very strong constraint on the two-point function of the primary and quasi-primary operator, as well on the three-point function, and on higher correlation function impose certain severe constraint. So I want to show that two-point function of quasi-primary operator of dimension delta, so now I'm focusing just on the z-bar part. I want to show you that as a result of the conformal invariance, this is going to be this unique form. So I want to prove it, that two-point function of quasi-primary operator has this unique form, and I put the normalization to be 1. This is my choice, because you see in any place where this field is going to appear will be always some coupling constant, let's say, associated to it. So it just matters how I'm sharing the normalization of these things. So I can always decide to normalize my field to be 1. Say different. If I have A here, I can absorb square root of A in each of them. All the relation I written down before will remain exactly the same. So the normalization is up to me. Okay? So I want to show that this is the case for two-point function. And the reason is I'm going to act infinitesimally. So infinitesimally, I'm going to make a transformation which says omega z is going to be z plus epsilon z. Now, epsilon z for Möbius, we saw the previous lecture that for Möbius, this guy can be at most a polynomial of order 2, cannot be anything else. Okay? So at this point, let me take this definition and let me see infinitesimally how a quasi-primary field is going to transform if I change my coordinate in this way. So what I'm going to do is z is equal d omega dz delta phi of omega z. So I use what I just wrote. So is omega z is equal 1 plus d epsilon over dz delta omega 1 plus epsilon z plus. So I'm going to expand because epsilon is infinitesimal. So the variation of the quasi-primary field under this transformation is epsilon d phi over d zeta plus delta d epsilon over dz times phi. Okay? So I have two pieces because I got one from here, which is this one, delta d epsilon dz times phi, and one which comes from expanding the field itself. Okay? So at this point, I have my two-point function and then, since it's a symmetry, the variation associated to it has to be 0. Okay? So I have delta phi delta 1 z1 phi delta 2 z2 plus phi delta 1 z1 delta phi delta 2 z2. And this has to be equal 0. So then I'm taking this definition, and then I'm going to do one by one, epsilon 0 different from 0, epsilon 1, epsilon 2 equals 0. Epsilon 1 different from 0, epsilon 0, epsilon. I have three differential equations. Okay? So I have three differential equations. So if epsilon 0 is the only one different from 0, the things I have is delta 1 plus delta 2 correlation function has to be 0. So this means that the correlation function can only depend on the difference. Okay? Now, if epsilon 0 is, epsilon 1, sorry, is different from 0, epsilon 0, epsilon 2 is equal 0, the differential equation you got is delta 1 plus delta 2 plus z 1 delta 1 plus z2 delta 2 applied to this has to be equal 0. So this is the Euler equation for homogeneous function of weight delta 1 and delta 2. Because if you derive your function multiplied by z, is as much as multiplying the function by delta 1 and delta 2. So this means that this function has to be something a z1 minus z2 delta 1 plus delta 2. Okay? And now I leave you as an exercise to impose the third one, the third equation. And you realize that imposing the third equation, since the function is already fixed at this stage, the only things that the third equation can do for you is giving a constraint on this constant. Do it. And the result is that two-point function, two scaling operator are orthogonal unless the scaling operators share the same dimensionality. This is an absolutely beautiful result, as you will see. Okay? So two scaling fields which do not have the same scaling dimension are orthogonal. Now, with the same token, exactly the same spirit, you can repeat the same exercise with the three-point function for the scaling fields. So here, once again, you impose that the variation has to be 0 because it's an invariance. And now let's arguing. Let's not even do the calculation. So symmetry means that we have 3 complex parameters that I can use to my will. 3. Now, with Möbius transformation, you can put 3 arbitrary points on the plane the way you like it. Okay? Now, once we do this on 2-point function, we find that using these 3 conditions, I can constrain the behavior of the function to be scaling low, and then the third one fix me the normalization. Now, with the 3-point function, I have 3 points. So this means that if I use consistently the symmetry, I shall be able to fix uniquely the behavior of this function in terms of the coordinate, but not its normalization. So from this point of view, I leave to you to prove the following, that phi delta 1, phi delta 2, phi delta 3, 3-point function, the form is C delta 1, delta 2, delta 3, Z12 delta 3 minus delta 1 minus delta 2, Z23 delta 1 minus delta 2 minus delta 3, Z13 delta 2 minus delta 1 minus delta 2, with the notation Zi to be Zi minus Gj. Clear? The mnemonic rule is very simple. The mnemonic rule is this guy should depend on all possible differences, so Z1, Z2, Z1, Z3, Z2, Z3, because it's a function translation invariant. Okay? Each of these differences should have a power law behavior, is in the nature of the theory. So the only things which remain is how to fix, or if you want, how to remember, with afterthought, what has to be the power on each of these channels. And the rule is very, very simple. Once you say 1, 2, you are leaving out 3. So the rule is delta 3 minus delta 1 minus delta 2. 2, 3 are leaving out 1, delta 1 minus delta 2 minus delta 3, and so on and so forth. Okay? Yeah.
Is this like a generalized version of Week's theorem?
Not really. Unfortunately not. No, I would say, seems analog, but better not to mix things. So, that being the uniquely dependence of the coordinate, remain a coefficient in front. Okay? Now, I claim that the coefficient in front, amazingly enough, is exactly the same structure constant of the theory. Can you give me an hint why I'm claiming so? So what I'm saying is, if you blindly solve these differential equations, imposing the first one, translation invariance, means has to depend on all possible differences. The second one gives you scaling property. The third one fixed uniquely the things. And since everything is linear, at the end of the day, the function is up to a constant. Now, previously, up to a constant, I used to absorb this constant in the normalization of the fields. So it was not a real constant. But in this case, I'm saying the constant which is in front is a real constant. It's some unknown. But even though it's unknown, this constant necessarily has to be the same structure constant which enter in the algebra. How you prove it?
Well, maybe think in terms of the on the if they get issue of these three and do it
Once. Either way.
you can use OP on the tree.
Okay.
And reduce one we get OP in terms of couples, then average and use the previous property.
Of normalization, of orthogonality. Clear to everybody?
Not so, because I would say that if I expand the OP between Phi1 and Phi2, I can obtain, okay, maybe Phi3, but also another operator which has non-trivial.
Okay. You are both right, but for different reasons. So your right is a quick way of saying. Is right in the sense that when you make the OP, it's not only one term, there are infinitely many. No. I'm talking about quasi-primal operators. Are very special operators, are not all operators. So this is the subtle point. So is right, when you make operator pro expansion of these things, you're going to get something, but infinitely many fields. And the orthogonality with things which is one, hold only for primary or quasi-primary. So the story is, I'm anticipating to you, that all the conformal field organize uniquely in families. So cannot exist a field conformal alone. Each field should belong to a family. Family of some primary fields. And we will prove it that the structure constant of all the fields in the family is proportional to the structure constant of the previous one. And at this point, Capizzi and make the story. Okay? Because there are only one, essentially, coupling constant with all the others which are proportional to it. Okay. Now, what about, so this means, great, my God, I'm solving the theory, I give you 2-point function. Remember, guys, that 2-point function in any field theory is hell. Think how you compute in any interacting theory 2-point function. It's completely hell. It's infinite sum of diagram as inside all possible singularity of the theory and this and that. So the fact that in this theory we are able to uniquely pin down the 2-point function, this is interacting theory, highly interacting theory. The fact that we are able to pin down uniquely 2-point function at once is an amazing result, as well as 3-point function is an amazing result. So you might get momentum by this success and say, wow, then I can solve any theory moving because now I can solve 4-point function. What about 4-point function? I take 4-point function here. I apply the same stuff. What I'm going to get? Unfortunately, not much, because Möbius has the property, as we say, the geometrical property of Möbius is to fix 3 points. So any 3 points on the plane you can put wherever you like. Typically, people put in 0, 1, at infinity. But this has 4 points. So this means that conformal invariance alone, omega, cannot fix uniquely the form of this function, but can only give you constraint. Indeed, what will happen is that this will be expressed in terms of some unknown function, but in terms of the so-called harmonic ratio of the theory. So what I want to say is that the Möbius transformation leave invariant a combination of the different distances. So in geometry, this is called harmonic ratios. So this ratio, there are many others, but this ratio, if you change map according to omega, the value is the same in any map. Okay? Since what you are expressing with this variation equals 0 is the symmetry with respect to that transformation, for 4-point function, the most that the theory can tell you is that this function cannot depend from Z1, Z2, Z3 in the most crazy way, but should depend only from the invariance of the group. Okay?
So if you apply Möbius transformation to those ratios, they will change.
Do not change. Yeah. So the result is for 4 points and higher point function, symmetry, apart some trivial prefactor, which is just question of how you parameterize the function, the non-trivial part is encoded into a non-trivial function, but this non-trivial function should depend only on the invariant quantity of the group. Okay? So it's exactly what, as we say in other time, if I give you the equation of motion of a wave equation of motion, what you can say is that the solution will be expressed in terms of an arbitrary function x minus t, as well as gx plus t. But the function is book, unless you have... So this is exactly the thing. So summarizing, 2-point function for quasi-primary and primary field is given. For 3-point function is given up to a constant, which, however, is unknown, because it's exactly the same which entered there. 4-point function and higher are constrained in terms of function which depend on the harmonic ratio. Now, I want to take the opportunity to introduce a language which will become very, very useful later. Now, this 2-point function, I want to interpret in the following way. Imagine that I define my theory on a cylinder. By the way, I can go from plane to cylinder through a conformal map. It's the logarithmic. Okay? Now, why the cylinder? Because the cylinder, in a very natural way, is the interpretation of space, let's say space coordinate, and time. Okay? So I'm going to use something like omega is equal log of z as a map. I'm taking out some L, something probably I have to do L over 2 pi. This is L. So cylinder has a natural geometrical interpretation of this direction to be time. And people in statistical physics use cylinder to make transfer matrix. Okay? So all this to say that I can think the evolution of my theory in time starting from minus infinity and going at plus infinity. Now, if I map this time evolution, which is here, is clear, in the original plane, what happened is that I got what is called radial quantization. Because at any radius r correspond certain cutting of time, with the minus infinity to be at the origin. Because I got minus infinity here if I put z equals 0. And plus infinity to be the ones outside. Okay? Now, if you want to define really the time evolution of a state, remember that you multiply a ht something, right, to make the evolution of a state. Now, imagine that you start from some initial states and then you want to arrive to the final one. So this means t infinity. Now, T infinity is pretty crazy because this guy just oscillates and stuff like that. So, what you do is a trick, is that in order, imagine, this is simple, but I mean, imagine that there are much more complicated things. In order to identify the states without dealing with these crazy oscillating things, you multiply by minus ht, you cancel this and take some limit. Okay? So what I want to say is that in order to identify the states, you take it out trivial evolution of the things. So let me define some states initial, like phi z applied to some vacuum, limit z goes to 0. It's a definition. I'm defining as states, applying my conformal field of dimension delta to a vacuum, and the vacuum is the only states which are invariant under the Möbius group. So this vacuum satisfies the following condition. Equals 0, L1 equals 0, L minus 1 equals 0. So this is the vacuum. Okay? So with this definition, I define this guy to be like that. Now, this is relatively simple. Less intuitive is to define the bra, because this has to do with the things at infinity. So for that reason, I'm saying you have to take it out, the evolution of this field at infinity, which in this case will be z 2 delta, apply to the field like this. So there is this extra factor here that take it out, let's say, the evolution under the Hamiltonian of your theory. Okay? Now, with this definition, what I want to say is that any relation in conformal field theory is a very pleasant story. You can interpret either as correlation function of fields or as a scalar product of states. So this relation I'm translating in the following relation. Okay? So I want to say that while in ordinary field theory there is a difference between states and fields, think for instance Dirac. There are fields which are the Majorana, derivative of the fields, whatever, but the particle, the states are only the fermions, the electrons. Okay? Bosons as well. Here, in conformal field theory, there is an isomorphism between all possible conformal fields and states, 1 to 1. To any conformal states, I can associate it a field, and vice versa, with this position.
So is there a Hamiltonian underlying the states?
Is what?
Is there a Hamiltonian underlying the states?
There is, yeah. I will. We'll see later, because the Hamiltonian, so your colleague is say if you have states, better to have an Hamiltonian to act on or to do something. And I'm anticipating, but I will derive. An Hamiltonian is nothing else than the integral of the stress energy tensor.
The energy part then of this.
Yeah, the energy. But I have also momentum, but so I will have, at the end of the day, a conformal Hamiltonian as far as I will have a concrete expression of the stress energy tensor, something that I will have. Okay?
We define the state as like the ket state, and then the definition of the graph is a definition, or we can prove that it's like the conjugate of the ket is the one with the limit and the z part.
Yeah, you can. No, okay. this guy is really the evolution according to the Hamiltonian, indeed. So the mystery will be, the Hamiltonian will play the role of L0. So this will be the Hamiltonian. The eigenvalues of the Hamiltonian is exactly delta. So if I act with the Hamiltonian on some primary states, I get the eigenvalues. So this is why I'm putting this. And I'm putting Z because going from the cylinder to the plane, the role of time evolution is played by Z, the radial. Okay? So, taking the moment as a blind definition, the real meaning we'll understand later when we'll define the Hamiltonian for my conformal field theory. And then, once we define this, you realized that this term is doing exactly what I told you. Namely, I'm using radial quantization where my time is Z. Anything which grows like this is like I'm moving on the cylinder, and I'm taking out the trivial evolution given by the Hamiltonian. Okay? Clear? But this will become clear, really net and clear later. At this time, give me for granted, because I want to show you essentially what I said, something very, very important, that there is a full isomorphism between conformal fields and states. And this is very, very helpful, either numerically, practically, logically, at all stages.
Just to make sure if I understood, that relation that we wrote for two-point functions holds for quasi-primary fields only, right?
Primary and quasi-primary fields, yeah.
Okay, fine. So what we're saying is that any conformal state is associated to a field, vice versa, but that expression we wrote is just for those.
For the primary, yeah.
The reason why you need a cylinder is because you need a compact variable, sort of, and then a freely expanding variable, then you define cuts. Like, why do you end up with a cylinder? Like, could you give intuitive?
No, as I said, the cylinder is a geometry where, first of all, we use all the time from statistical physics point of view. I mean, each time you have something defined with periodic boundary condition, or even not periodic means I introduce some extra fields. So, cylinder is the natural geometry where you define transfer matrix. When you have transfer matrix, one axis plays the role of time. So you want to put yourself in the familiar situation where there is some time evolution. It's just a question of to be on a safe side, to be in a comfort zone. Okay, so you want to have a time evolution better than cylinder? No. But once you have a cylinder, you can retrace everything in the plane simply by this analytic map. And since the theory has to be somehow invariant, we have to define this under this transformation. It should be something allowed. I'm not cheating. The theory is based on all these analytic transformations, so should be able to transform from one language to the other without any problem.
That is stricto sensu the primary branch of the logarithm.
Yeah. Okay, clear? Okay, equipped with this one, now we have to face the real problem. The real problem is what I did so far. I've exploited at the maximum level what I can get using just this. Now the problem is what to do with these other transformations that we know are not symmetry. Can we use nevertheless? Can we make sense nevertheless? Can I capitalize all the information which come from this? And so this is the content of the word identity, which we have to derive, okay? So, the next topic is how to deal with transformations which are not Möbius. So I will focus my attention on correlation function of primary fields alone The reason is that I know, and you will know later, that once you know correlation function of primary, essentially you own everything. So from this point of view, I focus directly my attention on primary fields. So I'm taking some primary fields here. Let me see to fix the notation. So here I'm doing in the full glory taking the dependence of the field Z and Z bar part. And one of the results of this word identity is that we will prove it that at the end of the day, the Z and Z bar part are splitted for what algebra is concerned. Okay, so this one will be one of the nice results of the story. So I have in the physical plane the point associated to the various Z1, Z1 bar, blah, 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 Zn part. So there will be some region which contain them all. So I take this radius, this circle, which contain all the point inside. Yeah.
We said before that we doubled the plane C2, so it makes sense to make inside this stuff. Right?
You have to be a bit cavalier. We are physicists, not mathematicians. So I'm using the plane as a physical plane. At this point, Z bar is the complex conjugate of the other one. Take it as it is. I'm not using Z bar, I'm using this point, which has coordinate x, Z plus Z bar divided by 2, y, Z minus Z bar divided by 2y.
Yeah, but the two points don't coincide, like Z and Z bar don't coincide.
I'm not coincide anything. I'm just saying this field has two coordinates. Do not coincide. This is the things.
Space in the double space or not?
Is the physical plane, x and y.
Okay.
Guys, are you cheating me or what? X do not coincide with y. Do not.
That's not what you have written though.
No. I'm just saying I make a change of variable and I denoted this point as Z and Z bar coordinate. Eh?
Yeah, it's R4, yeah. So there's no coincidence. That's not,
Exactly. I'm saying Z bar, Z and Z bar are just linear combination of these which uniquely identify one point on the physical plane x and y. So complicated? Oh, really? Is this?
it's still not rigorous, but okay, we can
But who cares? I mean, as far as the idea is clear, each point I need to have two of them because at the end I'm cosetting, right?
okay,
So,
that's clear.
yeah, okay. So I'm using the notation each point as associate two coordinates with this transformation. Okay. Okay, so now we said already that we cannot have a conformal transformation Z going to Fz and Z bar which goes to Fz bar, that they are different functions, that are small everywhere. It's impossible. Liouville theorem tells us that in the entire plane this is impossible. However, if I have a domain like this, I can cook up some generic transformation of coordinate, which is small everywhere. So I'm going to do r going r prime plus epsilon r, where these epsilon r are made in such a way that is an analytic function in the usual sense of the word inside this disk, and outside is small everywhere. And I connect the two the way I like it. Yeah. So the real catching point of the story is that, remember, even though the equation we derive seems to admit that any analytic map is good one, the catching point is that analytic map in the full sense cannot be small everywhere. So I want to bring myself to the condition where I can use infinitesimal transformation. And the trick is, once you have correlation function with endpoint, which are in the finite one, you will see how to deal at infinity later, but it's simple. I can identify a disk which contains all these points. And I can make a transformation of coordinate in the following way. Inside this disk, I can take to be an analytic function, regular, so no singular. Analytic in the full sense of Cauchy-Riemann story. But since I know that I cannot be small everywhere, when I arrive to the board, outside the board, I take a function which is differentiable, whatever it is, and goes to 0 very, very rapidly. Okay? So this transformation, therefore, is patchwork. So something analytic function inside the disk, and as move and goes to infinity very, very rapidly outside the disk. Okay? So at this point, there's going to be a variation of my action, because if there was a symmetry, the variation of the action is 0. But in this case, it's going to be something very, very explicitly related to the stress energy tensor, but outside the disk. I denote this as D2. Okay? Because if it was analytic, we derive already all the property, this term would be 0. Now, the conformal invariance is violated because outside the disk, I do not have something analytic satisfy Cauchy-Riemann, but another function. Therefore, there is this gradient. Okay? Clear? And now, the story is very simple. If I take this correlation function, let me define it in terms, let's say, of some path integral with some action. Okay? So you see, the way of deriving word identity, this is a general trick, is that this transformation, as far as is one-to-one, is just a reparametrization of your space. So the variation of your correlation function has to be rigorously 0. Because you're not changing anything. Any point that was before this was a new one. However, the variation now is made of two terms. There is a variation of the field which are inserted here, but there is a variation of the measure. Clear? Before, when I say there was an invariance, I just used that variation is 0, but I focus the attention only on the variation of the fields. If you take the notes before, you will see I just using variation of the field in any things. But now, when I do variation equals 0, I will have some variation of the field, but variation of the action. But variation of the action is ruled by this. Okay? This is what I'm going to use. Well, not yet. I mean, this is obviously something which is not invariant, so the theory is telling you, don't forget me, there is an extra term.
But intuitively, I think the action is a function of the fields again.
Yeah.
So why are you separating the fields? The fields are also subject to this transformation. Like, I see it as a bit of an artificial distinction. So like,
No, it's not artificial distinction. I mean, in general relativity, let me put it this way, each time you change a metric, is what I'm doing, the reaction is through stress energy tensor. Stress energy tensor is uniquely defined that way. Now, further step is eventually you want to express stress energy tensor in terms of some basic other fields. For instance, if you have Lagrangian, at the end of the day, stress energy tensor will be certain things. But it exists independently. It is the field which reacts to the variation of the metric.
the phi fields, though, precisely the phi fields. I mean, ultimately, the stress energy tensor will be a function of this phi.
Eventually, but here is very vague. I cannot even define for this theory a path integral. I'm just saying a way of formulating in a more familiar way is imagining that exists a field in terms of which you formulate the path integral. By the way, this field has nothing to do with that field I'm integrating on. Completely different fields.
What are those fields, though? What are those fields?
Guys, once per time, otherwise we don't understand anything. So let me clarify precisely what I want to do. What I want to do is focusing the attention on primary field the way I defined before. So these are very special conformal fields, are not generic fields, are very special fields. And then I want to express what happens on this correlation function if I make a change of variable which is small everywhere. This is what I want to control, okay? So the way of doing, I told you, is to have a transformation which is analytic in the region where they live, all the fields, and smooth and completely vanishing outside. Each time that I do this transformation, my action, so there is a change of the theory through this matrix change, is the insertion of stress energy tensor. So the stress energy tensor exists in the theory independently of any other things. Indeed, we will see that is the basic field. Now, if you have then the will to express in terms more basic field, your problem. But I am saying exists this field independent of what they are. And a way of understanding what I'm doing in a very comfort zone way is to imagine that my correlation function is obtained by in terms of some path integral or some fields which I have no idea what it is, an action which I have no idea what it is, and primary field which I have no idea how they are related to this field.
So these fields are not primary, so these generic fields are not primary.
So, you know, the path integral exists as a concept, but to implement it in detail is a question of things, okay? So the only thing I want to express is that when I make the general variation, which come up from this transformation, I have to take into account two terms. The variation of the fields, but also the variation of my geometry, if you want. Okay? Or if you like, the story you can rephrase like this. When you write something like this, you have to specify me which geometry you are computing in. If I make a generic change or transformation, this is going to be correlation in another geometry, which I denoted with these things. So what I'm doing essentially is these things is approximately this plus something, which is the stress energy tensor. deep down, I'm taking account how my geometry has changed. And from general relativity, I know that the field which react to geometry is stress energy tensor.
Okay, that's the reaction to geometry. Okay.
Okay. So if you don't like path integral, think that making a generic transformation, you have changed geometry. But since I'm doing infinitesimally, the new geometry will be equal to the old one plus the insertion of the stress energy tensor.
Metric. I changed the metric, you're saying. Okay.
Yeah. Clear? Yeah.
One thing is the variation of this guy zero inside of the disk?
Yeah.
Is that what you're saying?
Yeah.
Isn't f a generic analytic function? So why it's not a conformal transformation in a way?
Yeah, but it doesn't satisfy, this guy does not satisfy the Cauchy-Riemann equation outside. And therefore you have a term like this. Is D2, the integral is in D2, it's outside.
I'm just confused by why it should be zero inside.
Because was analytic and small. Satisfy Cauchy-Riemann. This guy inside satisfies Cauchy-Riemann. So I'm precise in the condition of Polyakov theorem. Is small, and so done. Please.
So, okay, I kind of don't really understand how we want to describe the arbitrary analytic function which is not small by having small analytic function.
I'm not describing small analytic function. No. I'm doing a small change of variable, physical plane. Now, plane does not mean complex plane. Plane means plane. To have a complex function, you need extra condition, Cauchy-Riemann, okay? So here, I'm just doing two-dimensional plane, the physical one, a new coordinate. That's it. But this new coordinate, I can take it to be analytic function inside this disk, only inside. Small. Inside, but small, and only there. Okay? So if you take z square, or z cube, which is analytic but not small everywhere, as far as my disk is 1, at most can be 1. I put an epsilon in front, I can take smaller as you like. Okay? So this generic transformation, inside I will take to be analytic function which satisfy Cauchy-Riemann, small to my will. Because whatever function, I just put an epsilon in front. You take the most crazy analytic function as far as there is no singularity there, I put an extra constant in front and take it small as I want. So this is what I'm doing. Outside cannot be, because otherwise I would have found analytic function small everywhere. So outside has not to be analytic at all. So I have a breaking of conformal invariance outside. Okay?
But you assume that the correlation function does not change because all the points are inside.
Yeah. Yeah.
And it goes to zero inside, not to infinity, right?
At infinity goes to 0.
Oh, okay.
Rapidly, the way you like it. Okay?
So that's like this is not an analytic continuation.
No, guys, you are giving me really hard time. I mean, it's the most simple concept of the world. I'm just taking change 1 to 1. Can be crazy as you like. The only thing I want to go to 0 so that I can make integration by part. It's the only thing I needed. The only bloody things I needed to integrate by part. Then they can go with a cusp. They can go with a jump. They can go wherever they like. I don't care. Okay? As far as there is a one-to-one mapping of all points of the plane. So this means that all the points of these things get mapped into themselves. All the points outside are mapped into themselves. How they are mapped? Okay? So please let me go, because if I spend half an hour just explaining this, we are done. I mean, we never finish anything. So, what I want to say is that the delta has to be 0, because I didn't do anything. The only thing now is that I have two terms. So the variation of my correlation will be sum on I delta I di epsilon plus epsilon delta I plus delta bar I delta bar I epsilon bar plus epsilon bar delta I. So if it was just for that, that will be the variation of my fields as I did in 2-point and 3-point function. But then plus 1 over 2 pi integral then 2r then mu epsilon nu and all this has to be equal 0. Okay? So the fact that these things has to be 0 with respect to before is expressed by the fact that I have variation of the fields under this transformation plus insertion of this extra term. Okay? So what I have to do now is to handle this extra term. So since this is an integral on the plane, I can use the divergence theorem. The integral on the plane is equal to the integral on the surface. Here there are two surfaces, one at infinity and one on the disk. At infinity I want to be 0, so this is why this bloody epsilon has to go to 0, faster than 1 over z4 if you want to be precise, and remain just the integral on the disk. So 1 over 2 pi integral on d2 d epsilon this is equal minus 1 over 2 pi d2 I invert epsilon nu x derivative of these fields plus 1 over 2 pi integral on the surface n nu epsilon nu t mu nu blah blah blah. Okay? So what I'm doing here, I have to integrate in this region. I integrate by part, and then I have to collect the term on the surface. This term of the volume is 0 because my stress energy tensor in any way is conserved. So the volume is nothing and remain integral here and integral at infinity. Integral at infinity I disregard because epsilon is going to go very fast. So what I'm going to say is that this term which enter this equation is nothing else than an integral on this surface with my function computed there and the normal to this surface. And now we have to rely on the fact that in our theory, which is conformal invariance, namely scaling invariance, we know that the field is conserved, symmetric, and traceless. Remember. So there are only 2 independent components out of 4. So I can make linear combination, which are this one. Okay? So my original tensor was T11, T12, T21, T22. T12 is equal to T21 because it was symmetric. traceless, so T1 plus T2 is equal 0, so this guy essentially is twice T1, 1. And then I am anticipating that if you do this linear combination, the component of the stress energy tensor, by the conservation law is T mu nu equals 0, you can prove it immediately that the conservation law of this is equivalent d z bar of Tz is equal 0. Means that this field doesn't depend on z bar. On the other hand, if you do the other one, dz of T z bar is 0. Okay? You have to do it. I'm saying that if you take conservation law, you make the change of variable I told you before, x is equal z plus z bar half, y is equal z minus z bar 2i, and you express T mu nu equals 0, this conservation law, and apply to this, you realize that this field, even though before you might think depend on z bar, as a matter of fact, the conservation law tells you that depend only on z. And this guy depend only on z bar.
So there's a question. What do the indices 1 and 2 refer to?
Is the index 1 and 2. Yeah. Okay? So I'm in the plane. I have two coordinates. So you can have conservation, which is delta 1 blah, plus delta 2 equals 0. If you make a change of variable and go in z bar variable, you realized that this conservation law, the stress energy tensor, apply on this combination is telling you that this field depend only on z, and the other one depend only on z bar. And there are only two independent components of the stress energy tensor. So all this to say that this surface integral, with change of variable to parameterize the circle, I can write it down in terms of Cauchy integral, namely is 1 over 2 pi integral c d sigma n nu epsilon nu t mu nu. This one I can write down as 1 over 2 pi I integral dz epsilon z tz whatever is here minus 1 over 2 pi I d z bar epsilon z bar t bar z bar blah blah blah. Okay? It just a change of bar. This surface on this integral on a surface, I just convert smartly in an integral on complex variable. Okay? Because the radius is fixed. So dz is as much as the angle. And at this point, coming back to my previous equation there, we realize something very nice. First of all, you see that the z and z bar part are completely decoupled. So we have delta E, which depend on just the this is equal to 1 over 2 pi I integral dz epsilon z tz the field. So if you combine the two parts, So you see that there was one term here which is fully analytic, and this term here which is fully anti-analytic. So this term should go with this part of the stress energy tensor, and this term should go with the other one, because there are epsilon z and epsilon bar of z which are arbitrary. So in order to be identity, it has to be identity one-to-one. Okay? But we are not done yet, because we have to remember something of analysis. How to compute the derivative of function in terms of contour integral is a double pole. So this term here, this right-hand side, left-hand side, I can express as sum on I integral dz over 2 pi I epsilon z delta E z minus z square plus 1 over zi di. Okay? Clear, everybody? In complex analysis, you can refer to the value of a function and derivative of a function in a point as an integral around that point. Okay? So, in order to get the derivative of epsilon, I just have to integrate epsilon with a double pole. In order to get epsilon itself, I have just to integrate a simple pole. Now, why am I doing so? Because, as is written here, I have an equation which is differential on the left-hand side and integral on the right-hand side. Here is an integral. So I want to refer everything local. So if I do so, comparing, I arrive to the beautiful word identity which says Tz apply to a primary field 2 as an operator Fourier expansion which is okay. So let me make more explicit what I'm doing. I want to convert this relation in something local and moreover of the type of operator Fourier expansion. Once I convert the differential operator here in terms of pole things, now I'm on the same level. Integral is on the left-hand side, integral is on the right-hand side. Epsilon is arbitrary, so should hold point by point. Yeah. So what this identity is expressing is the operator Fourier expansion of T with the field delta is given by an operator Fourier expansion which involves at most a second order pole plus some regular term that we are unable to determine, because all integral is blind to all regular things. So, the net result of this is that I'm presenting you the first explicit operator Fourier expansion of the theory, which involved the stress energy tensor and a primary field. Remember that one of our basic things was I have a scaling fields that has to fulfill some operator Fourier expansion here, okay? And I say we have to determine the structure constant, we have to determine the blah, blah, blah. I'm telling you, if you refer here, I've derived for you the first non-trivial and non-empty operator Fourier expansion of the theory, which involved the stress energy tensor, a primary field, and the left-hand side. The left-hand side, we see that in the operator Fourier expansion, these two guys always appear the same guy, and derivative of it. Okay? The structure constant here is delta, and here is 1. Moreover, the anomalous dimensions are proper because stress energy tensor is the field in the theory whose anomalous dimension is always 2. Because if I integrate it, I have energy. And energy is non-anomalous never. So the stress energy tensor has dimension 2. And you see that it matches perfectly. On the left-hand side, I have a field 2 plus delta here. And here, I have a field 2, and this guy is delta. So things are matched. Here is one pole, but the derivative, take it another dimension, delta, and the scaling of delta is matched left and right. Okay? Clear?
Is this just for primary fields?
Yeah, it's a primary field.
And is the expectation values you drop?
No, yeah. Because, thanks, because remember, any operator expression going to write is meant to be in correlation function. So it's an abuse of language. I should have make in correlation function. Correlation in the sense is it holds in correlation function, but the rest here is completely arbitrary.
So basically the theory only allows me to treat it. I mean, the theory only allows us to treat expectation values at the...
Yeah. So I'm just saying this is section number 1. I said any operator expression I'm going to write, you have to meant inserted in correlation functions. Yeah, but not correlation function the way they are. Correlation function means there is something completely arbitrary here. So it means they hold generally. Okay?
Why cannot I also throw away the path integral and just get an identity for the field itself?
You can do it. It's what I said before to him. If you don't like the path integral, fine. But then making a transformation the way I did, you are changing geometry. So cannot be the variation of the field alone, because in this correlation function enter also the change of geometry. And when you change geometry, the reaction to a geometric transformation is the stress energy tensor. Okay?
Is this the definition of the stress energy?
It is a definition, yeah.
So we're putting in gravity.
Exactly. So this is before because he wanted the stress energy tensor to be field of a field. Fine, but there exists a meaning in itself of the field, which is just the response of your theory to a change of matrix. So it's a definition, yeah. Okay? So this is the word identity. The word identity is that any variation of the metric involve an insertion of the fields, and then if you bring to the extreme consequences, we end up to the first non-trivial operator pro expansion of the theory. Now, primary field are those fields which are selected out by the fact that the stress energy tensor, when you make operator pro expansion with it, the power that you get is the mildest as possible, namely second order pole. If you take an arbitrary scaling field and you make operator pro expansion of the stress energy tensor, you might have pole of arbitrary order. This is the main distinction. So quasi-primary has the mildest operator pro expansion compatible with everything. Okay? And has to be true, cannot be anything else, because the anomalous dimension of these things is 2. Remember, the power law here is constrained to be delta n plus delta m minus delta kappa. And you see that delta n in this case is 2. M coincides with kappa, so you cannot have something less than second order pole. Something less is not allowed. You can have something more, but not something less.
Yeah, but sense, the second order term arose from the derivative of epsilon,
Yeah.
which is linearization. So in effect, like I cannot see, could you trace it back to being primary? Like, so when we involve explicitly the primary of the field in this derivative of epsilon, could you go a few steps backwards?
You remember how was the variation of the field, primary? Has two terms. This was delta df over dz plus f dz. So this term comes exactly from there. Because remember there was a weight, but then you are also translating the coordinate. So there are two terms in these things.
Otherwise, I would have had higher order derivatives and higher order divergences.
Yeah, sure.
Could you specify again what is the meaning of the terms that you were neglecting in the expression? That they cannot be constants, you said?
Oh, each time that I gave you an integral of, in complex analysis, integral is only sensitive to singularity. If you integrate any polynomial, are always zero. So this means that if I want to go from integral identity to pole identity, I can only make commitment on the pole. But on the regular part, I have no commitment as far as this equation is concerned. Doesn't mean that these are arbitrary, not at all. The only thing it means that I cannot fix from this equation. Later, I'm going to fix uniquely all of them. Okay? Okay, so that being given, now let's make further progress. So the main things here is that we have met the stress energy tensor. Now, stress energy tensor in conformal field theory has a very, very peculiar role. The peculiar role is that it is simultaneously referee and player. In the sense that you rule the transformation. Each time you make a transformation, poof, you have to insert T. But is a scaling field as any other. So it has two roles. From this point of view, I can pose what is the operator for expansion of T with itself. So, let's see what it can be. So this guy, you can prove it, is a quasi-primary field of dimension 2. Therefore, there should be, for sure, by the rule I just derived, the second order term. Okay? Because T here is a quasi-primary field. Yeah.
So the fact that the stress energy tensor is a scaling field is an assumption, or we can?
No, you can prove it. No, come on. I mean, yeah, sure. I mean, because the correlation length is infinity. I'm basing all my theory on that. Yeah, has to be. Yeah. It's traceless. As dimension 2 cannot be anything else. Any field has to be scaling field, just by the construction I'm doing.
But then we can also prove that it is quasi-primary.
Yeah. Then you can show that if you make change of variable, this is a bit, if you want really to put your finger, you have to be a little concerned, because I'm doing everything in Z and Z bar variable in Euclidean, and so if you want to trace everything, we put all the dot on all the I. It seems that this class really concerned with all the dot on the I. You have to go to Lorentz. You have to make a change of variable which goes to Lorentz in Minkowski. In Minkowski, everything is well defined, blah, blah, blah. And so you carried on everything and then you prove it. Okay? So this is the way, but we have no time in doing that. So I'm saying that this equation hold for any field of that type. So this term has to be there because the stress energy tensor is dimension 2. The point is, can I have something higher order here? And the answer is yes. The answer is, can exist a 4th order pole here, and this shows that the field is not primary. Why exists something like that? For very good reason. Because if I do now 2-point function, and nothing else, so here I'm referring, hello? You. So before you're asking, is in correlation function? Yes, I reply. Correlation function means arbitrary insertion, so it has to be an operator identity. Here, I'm matching really 2-point function. Okay? So if I match 2-point function, I have to take something like this. I told you that expectation value of any scaling operator, but the identity are 0. So this term here either is 0 if this term were not there, or if it's there, it has to be uniquely this one. There is no other way. We see an arbitrary parameter. Why so? Because these guys, as you immediately understand, if I insert here a complete set of states, whatever they are, this quantity is intrinsically positive. This quantity is infinite sum between the vacuum and a bunch of other terms. So this term is non-zero. It cannot be 0 by summing negative and positive term. It's intrinsically positive. So it has to be non-zero. The only way it can be non-zero is that in addition to this term, there is this extra term here. And I parameterize this in terms C over 2. C is a constant. It's called central charge. Okay? So the central charge is related to the 2-point function of your theory. Okay? And now I have a very beautiful relation, which is this one. So TT is C over 2 Z1 minus Z2 4 plus twice Z2 square plus 1 over Z1 minus Z2 dt. And now what you can do is something extremely interesting. The other nice things about conformal field theory is that any operator product expansion you can convert in ordinary commutator on anti-commutator relation. These are very nice things. So whatever commutation you can rephrase in operator product expansion and vice versa. So in this case, let me expand T around the origin in terms of mode. Okay? What are ln? Well, ln, you see immediately, is 1 over 2 pi I integral dz zn plus 1 tz. Okay? So imagine that I want to compute ln lm. So I have to do the first integral. So I have to do 1 over 2 pi I integral C1 d eta n plus 1, and then d C2m plus 1, and then insert 2t. Okay? So this is this term. I'm doing this integral. Okay? Now imagine now that you want to compute minus ln ln, alias I want to compute the commutator. ln ln. So in order to compute this term swapped, the only thing I have to do is to take this contour and bring it outside. Right? But now the point is when 2 points of the contour coincide, I have the operator pro expansion. So the difference between the two contours is going to be equal to the contour times the residue at the pole of coincidence. Clear? So if I swap, so let me say pictorially, this one minus this other one, where this is equal this times this. Okay? Tell me.
Even in the first expansion, how is the contour C1 defined? Like, liquid defined like?
Is Cauchy-Laurent contour. Is circle. I mean, it's how you define the expansion of a series. Okay? Now, I leave to you to do this exercise, a beautiful exercise. Beautiful. If you try, you don't succeed, you open my book. But please try yourself. So what I want to say is that out of this turns out this beautiful algebra. Okay? So, summarizing, equivalently to the operator pro expansion, the stress energy tensor, equivalently, an equivalent information is to pose exists an infinite number of operators, which by the way are the mode of T, which satisfy this commutation relation. And then just looking at this, you realize that it is exactly like the previous algebra or the conformal transformation plus an extra term. And this extra term is due to this stress, to this central charge. Okay? So if central charge is different from 0, you have this extra term. Now I have to prove next time, now we have no time, that indeed the C you can interpret as an anomaly. Because if I do a transformation, something has to be 0, on the other hand is not 0. And what is not 0 is ruled by C. I will show you next time. So this will put C under the footing of an anomaly of the transformation. But here I want to say that as the same information is here, it's here. And therefore we got the very first conceptual point of the story, that to classify phase transition and critical points, we have to find, finally, the irreducible representation of an algebra. It's really an incredible conceptual point, because put the problem on the same level if you want to understand the property of the space under rotation. How you solve it? You have to find all possible reducible representation of SU2. Okay? So it's a very important conceptual point. Everything now is encoded into an algebra. And next time we will play with the irreducible representation of it.